I've given you a very long and complicated definition of L'Hopital's rule, but the application of it is very simple. So, f and g are functions that are differentiable on an open interval. So f and g, you can take the derivative of both of them. And they contain, on this interval containing c, and they are differentiable everywhere except for possibly at c itself. So you can take the derivative of f and g, but it's possible that maybe it's not differentiable at that point at c, because sometimes you get zeros whenever you do that. So we're assuming that the derivative of g does not equal 0. That's going to be important because you see that derivative's in the bottom, and we cannot have zeros in the bottom. For all x in AB, if the limit of f of x over g of x as x approaches c produces the indeterminate form. This is the big thing that they really stressed when I went to that last training. Right here we see that it says if the limit as x approaches c produces the indeterminate form, then we can say the limit as x approaches c of f of x over g of x is the same as the limit as x approaches c of f prime of x over g prime of x. Now, it's really important that it must produce the indeterminate form. Now, we have so far just said the indeterminate form was 0 over 0. There are a few other types of indeterminate forms. If you get infinity over infinity or negative infinity over negative infinity, that is also an indeterminate form. So you may want to pay attention down here. Not only are we talking about 0 over 0, but infinity over, infinity or negative infinity over negative infinity. So L'Hopital's rule does not apply if you do not get the indeterminate form when you use direct substitution. So, I showed you just a little bit of this when I came back from that training. Not how to do this, but just to show you, for every single one of these, and I want you doing this in your homework as well, you must first check to make sure that you get the indeterminate form. Because if that does not happen, then L'Hopital's rule does not apply. So, the first problem that I have here is one that we could solve without L'Hopital's rule pretty easily, because I could say that this is limit as x approaches 4 of 3 times x minus 4 over x plus 4, x minus 4. I could factor, and I could cancel my x minus 4's. And so now if I plug in 4, I get 3 over 4 plus 4, which gives me 3 over 8. So that one can be solved without L'Hopital's rule. If you get this problem on the AP exam, there's no need to do L'Hopital's rule. However, if we look at some different problems, we're going to see that that's not always the case. Now, a lot of these I've given you just ones that you can use other methods on, mostly because the other ones are hard to come up with, and I just had to stick with things that I knew. But we'll just look at these. So if we're going to use L'Hopital's rule for this, we must first show that this equals the indeterminate form. And this is where I showed you when I came back from that training. I have been letting you guys do this. In fact, I have been doing this myself. So don't write this down right now because this is bad. Okay, so don't write what I'm writing right here. So we're not going to write this down, but I've been saying, oh, if you plug in 4 in the top, you get 0. If you plug in 4 in the bottom, you get 0. So this equals 0 to 0, which is indeterminate form. I've let you guys do that. I have done this myself. They have told me at the AP training that if you do this, you will not get credit. Because nothing can equal 0 over 0 because it's indeterminate, and you can't equal something that doesn't even really exist. So we cannot do that. So even in our homework, even though it's a pain, because we knew good and well what we were talking about whenever we did it the other way, on the AP exam, we have got to say the limit as x approaches 4 of 3 times x minus 4 equals 0, and the limit as x approaches 4 of x squared minus 16 equals 0. So we cannot say that this limit equals 0 over 0. Instead, we can say the limit of the top equals 0 and the limit of the bottom equals 0, and then that tells us that we have the indeterminate form. I feel like this is a major technicality. I don't even really like that they make you, that they won't let you write that, because I feel like you know what you're doing whenever you do that. But we have to write it this way on the AP exam. So on your homework, I want it written this way. And I want you to write this every single time. Okay? Because if you don't, then you cannot get credit for your L'Hopital rule stuff on the free response questions. And I feel like it's definitely going to be on there somewhere in the free response questions. It was on there last year, and they've been stressing it in those trainings and in the stuff that they've been putting out through the College Board. So I feel like it's probably going to be there again this year. So we want to make sure that we get this right. We're going to write this every time, even in our homework, even though it's annoying. So this you must show before you can use L'Hopital's rule. But L'Hopital's rule tells you this, that if you have the indeterminate form, then you can do this if you would like. So let's say it's something difficult to factor, or maybe something that you can't factor at all. You can do the limit as x approaches 4 of, we can take the derivative of the top, which is just going to give us 3x, and the derivative of the bottom, which will give us 2x. And then we could plug in our numbers, or in this particular case, your x's cancel, and you get, hold on, something's wrong. Oh, I know what's wrong. What did I do wrong? It should just be 3. No x with it, because you're going to have 3x. The derivative of 3x is just 3. And the derivative of the bottom is 2x. So if you plug in 4, 3 over 2 times 4, it's going to give you 3 over 8. This works on pretty much all the problems we've done, except for things that you were going to have to use direct substitution on. Direct substitution does not give you 0 over 0, so you cannot use L'Hopital's rule for that. But pretty much all the other limits that we have done, you can use L'Hopital's rule on them to solve those limits. So this particular problem, anybody know the answer to this one without doing L'Hopital's rule? We should. It is 0. Why is it 0? It's bigger on the bottom. This is the limit as x approaches infinity. So you could do this one with Bobo-Botno. If you get it on the exam, use Bobo-Botno. That's fine. But we also could use L'Hopital's rule for this, and since that's what we're learning today, we're going to use L'Hopital's rule. So the limit as x approaches infinity of 2x minus 7. Now look at this. This is a little bit different. You're going to get 2 times infinity minus 7 whenever you plug in infinity, if you can. I mean, you really can't. But so 2 times infinity would be infinity, and then you could subtract 7, but it's still infinity. And you could do the limit as x approaches infinity of 3x squared minus 9. And so you got the same thing going on here. You got 3 times infinity squared minus 9. Infinity squared is infinity, then multiply it by 3, still infinity. Subtract 9, it's still infinity. So you get infinity over infinity for this problem. Now, I find this kind of interesting because if I had asked you before what infinity over infinity was, what would you maybe say? 7 over 7 is 1. 9 over 9 is 1, 10 over 10 is 1, 1,000 over 1,000 is 1. one would be inclined to say that infinity over infinity is also 1 because it's something divided by itself, but it is actually an indeterminate form, so it does not equal 1. So this is indeterminate form. That means we could use L'Hopital's rule, so we'll have limit as x approaches infinity of 2 over 6x, and so that's going to be, as we do this here, it's going to be 2 over 6 times infinity. So as x approaches infinity here, the bottom of that fraction gets bigger and bigger and bigger and bigger and bigger. So what does our value approach? It will be 0 for this. So you got 2, which is a small number, over a really, 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 really big as you can get big number, which is basically 0. All right, questions? Okay, here's our next one. Now there are sometimes, like this particular problem, we could rationalize. Or, now that we know this, we could do the limit as x approaches 0 of the square root of 25 minus x squared minus 5, and say that that equals 0, which it does. And then we could say the limit as x approaches 0 of x equals 0 here. Again, to me, it's all on multiple choice. You don't necessarily have to write that, but on your homework, please do, because we need to be in the habit of that. So since you get the indeterminate form, you can use L'Hopital's rule. So you can do the limit as x approaches 0 of, this is 25 minus x squared to the 1/2. So we would have 1/2 times 25 minus x squared to the negative 1/2. And then we'd have to multiply by the derivative of the inside, which would be negative 2x. Use a chain rule there. And then derivative of 5 is just 0, so it goes away. Over the derivative of x, which is just 1. And so that gives me the limit as x approaches 0 of, let's see, that 1/2 and that 2 will basically cancel out. So in the top I'll have negative x. In the bottom I'm going to move that square root of 25. Minus x squared back down to the bottom. Thank you. And so if I plug in 0 now, I get negative 0 over the square root of 25 minus 0 squared, so I get 0 over 5, which is 0. Now, I don't necessarily think that is easier than rationalizing the numerator like we've been doing so far. Not necessarily too much harder to do either, but we could use this on this. So example 4 starts to get into where we really need to be able to use L'Hopital's rule, because if I do the limit as x approaches 1 of x to the 11th minus 1, I get 0. And if I do the limit as x approaches 1 of x to the 4th minus 1, I also get 0. So I have the indeterminate form here, but I cannot factor that. I cannot rationalize. I mean, I can factor the bottom. There's probably some sort of crazy factoring rule that you could use for the top, but none of us know it. I don't know how to factor any difference of 11ths. So we can't really take we cannot take the limit of this, knowing what we know. But we could use L'Hopital's rule, so limit as x approaches 1 of 11x to the 10th over 4x to the 3rd. If we take the derivative of the top and the bottom, now we could plug in our 1, so we'd have 11 times 1 to the 10th over 4 times 1 to the 3rd, and we would end up with 11/4 for our answer there. Now, if they're asking you to use L'Hopital's rule, it's more likely you'll see a problem like this where you have to use L'Hopital's rule. But it can be used on anything that gives you the indeterminate form. Okay, questions? Okay, we've got a few more to do. Here's our next one. Example 5, we must always show our limit as x approaches infinity of e to the x. What is the limit as x approaches infinity of e to the x? What would we get, Harper? It'd be infinity. Because e to infinity would just be e to a really big power, which would be a huge number. And so limit as x approaches infinity of x to the 3rd, same thing's going to happen here. Infinity to the 3rd power is still infinity. So we have infinity over infinity, which is indeterminate form. So we could take the derivative of this. So if we do that, we could say that this equals the limit as x approaches infinity of e to the x over 3x squared. Now here's the problem. If we plug in infinity to that, if we do the limit as x approaches infinity of e to the x, we get infinity, and if we do the limit as x approaches infinity of 3x squared, we also get infinity. Still indeterminate. Still don't know the answer. But we can apply L'Hopital's rule more than once. So we could take the derivative again here. So if we take the derivative again, we'll have the limit as x approaches infinity of e to the x over 6x. We still have a problem here, infinity over infinity. So notice every time I'm writing this junk, I promise if it was up to me, I really wouldn't make you write this. But there are some instances where you have to notice, and the AP exam, they're going to make you write this. So every time you got to show it's still infinity over infinity. It's still infinity over infinity, so we can take the derivative one more time. And so the limit as x approaches infinity of e to the x over 6. This time you will not get infinity over infinity. Instead, this time you'll get infinity over 6. And what is infinity divided by 6? It is infinity. If we had a negative 6 in the bottom, then that would be negative infinity. So the multiplication and division rules still apply as far as signs go. So if you're multiplying by a negative or dividing by a negative, that will make it negative infinity. Or if you had a problem where it was like 2 minus infinity, that would be negative infinity. Now, you kind of could have used Bobo-Botno on this because although they don't have e to the x and x to the 3rd power, those are not, they don't have, it's not like having x to the 5th and x to the 3rd. E to the x is like having a higher exponent than any possible x to any power, so it's bigger on top. Okay, so, unit circle. limit as x approaches 0, sine of 5x. That is just going to be sine of 0. What is sine of 0? It is 0. Okay. The limit as x approaches 0 of tangent of 9x. That would just be tangent of 0, which is also 0. It's sine over cosine, which is 0 over 1 for that. So you get 0 for that as well. So we've got 0 over 0. We can use L'Hopital's rule because we've got no other choice. There's nothing else we know how to do with this trig stuff. Even if we tried to use trig identities, it's not going to work because we got a 5x and a 9x. If they were both 5x's, then we might could do some canceling to get things to work out here. But a 5x and 9x, nothing's going to cancel. So instead, let's take the derivative of the top and the bottom. So derivative of sine of 5x would be cosine of 5x. But we do have to use the chain rule here. So we have to take the derivative of the 5x, which would be 5. So we put that 5 out here. And then tangent, what's the derivative of tangent? Secant squared. So secant squared of 9x times the derivative of 9x, which is 9. Now we can plug in because we've got 5 cosine of 0 is what we get when we plug in the top. And what is cosine of 0? It is 1, so we just get a 5 in our numerator. In the denominator, we're going to have 9 secant squared of 0. Remember, secant is 1 over cosine of 0, so 1 over cosine of 0 would be 1 over 1, and then we're going to square it. It's still going to equal 1, so we get 9. So we get 5/9 for this problem. Okay, questions? Okay, here's example 7. There is a way that we could do this without using L'Hopital's rule because we did learn long ago. Anybody remember the limit as x approaches 0 of sine x over x? Anybody remember what that was? No. So that's a good reason to use L'Hopital's rule on this. I like L'Hopital's rule because it's a process rather than having specific things memorized. But this equals 1, so in the olden days we would say this part right here equals 1, and then cosine of 0 is 1, and so 1 times 1, and so C would be the answer. But that requires you to have this memorized and not to apply it incorrectly somewhere else. So we can use L'Hopital's rule on this problem. Although first we must show that the limit as x approaches 0 of sine x cosine x equals 0, which it does. And we must show that the limit as x approaches 0 of x equals 0, which of course is evident there. So if we use L'Hopital's rule here, we could say that we're doing the limit as x approaches 0 of, we've got to do a product rule for our sine x, cosine x. So we'd have sine x times the derivative of cosine x, which is negative sine x, plus cosine x times the derivative of sine x, which is cosine x, all over the derivative of x, which is just 1. And so here we've got the limit as x approaches 0 of negative sine squared x plus cosine squared x. I could put that over 1 if I want to, but I don't have to. And so if we plug in 0, negative sine squared of 0 plus cosine squared of 0. If we take sine of 0, it is 0. 0 squared is 0, and negative is still 0. Cosine of 0, on the other hand, is 1. 1 squared is 1. So we end up with an answer of 1 for this problem. If you remember this rule right here and how to apply it, it is faster to do it that way. But if you don't remember, then L'Hopital's rule is a good one to turn to. Okay, questions? Now the next couple are really what you're probably likely to see on some AP exam stuff or possibly progress checks that we're going to be looking at tomorrow. So AP exam loves to give questions like this, where you've got no choice but to use L'Hopital. Plus, they love to give problems where you've got to look at a graph or a table to find some of the stuff that they are asking for, and it's very theoretical because you got to know how to take this derivative, even though you don't know exactly what this part right here of it is. So, to do this problem, we would first still have to show that the limit as x approaches 0 of 2f of x e to the x plus 4 equals 0. So, you'd have 2 times f of 0 e to the 0 plus 4. What is f of 0? It is right here. Y coordinate is negative 2. So we've got negative 2. And e to the 0, anything to the 0 power is 1. So you'd have negative 4 plus 4, which does equal 0. So that tells us we get 0 in the top part. And then in the bottom part, if we do the limit as x approaches 0 of 3x squared minus 3x, if we plug in zeros there, we just end up with 0 minus 0, so we get 0. Well, the AP exam, they're not going to be picky on things like whether or not. Like on that first problem, I showed a lot of work in plugging everything in. That was mostly for my own benefit, so I could keep it all sort of straight in my head. In the second one, I didn't show any work because I did all of that in my head. They're not really very picky on whether or not you show all the steps to getting just basic arithmetic sort of answers, but they are very picky in that you better write this stuff right here before you use L'Hopital's rule. If you leave this part off, then you're going to not get credit for the problem. So now that we've shown that we get the indeterminate form, now we've got to take the derivative. The derivative is much more difficult than some of the other ones that we have been looking at, and you've got this f right here to deal with. So we're going to have the limit as x approaches 0 of, we've got 2f of x and e to the x. We've got to use a product rule for this. So we'll have 2f of x times the derivative of e to the x, which is e to the x, plus e to the x, times the derivative of 2f of x. What is the derivative of 2f of x? What is it, Wendy? Good. 2f prime of x. And then what's our derivative of the 4? It's 0, so it goes away. In the denominator, it's much more simple. We'll have 6x minus 3. So at this point, we're plugging in 0 for all of these. So we've got 2f of 0 times e to the 0 plus e to the 0 times 2f prime of 0 all over 6 times 0 minus 3. And so we've got to find f of 0. What did we say f of 0 was? We've already used that once. It is negative 2. So we've got 2 times negative 2. E to the 0, what is that? It is 1. So we'll have another 1 right here. F prime of 0. What do we have for f prime of 0? Almost. What did you say, Harper? Negative 1. So it is the slope of the tangent line, right? Derivative gives the slope of the tangent line. It is negative since it's decreasing here. So we'll have negative 1 all over. That's going to give us negative 3 in the bottom there. And so this limit is going to be negative 4 minus 2 over negative 3, which is going to give us negative 6 over negative 3, which gives us positive 2. We get positive 2 for our answer. Okay, questions? All right, and here's our last one. Oops. So this time we've got a table. We're going to have to do more or less the same thing that we just did on the last problem, but instead of referring back to our graph, we'll refer back to our table. We must, for every problem, show that we get indeterminate forms. So we've got 2, the limit as x approaches negative 1 of 2x f of x plus 5g of x. Notice I am not plugging in the negative 1 right there, because when you're taking the limit of something, you don't, it's only over here on the other side of the equal sign that you actually plug the number in. So you got to do 2 times negative 1 times f of negative 1 plus 5 g of negative 1. Oh, and there's a mistake on this table right here. This x right here needs to be negative 1, because if it's not, it doesn't make any sense at all. And so if we do that, we've got negative 2 times f of negative 1. F of negative 1 is going to be 5 plus 5 times g of negative 1 is negative 2. Oh, I've messed up this problem. I think this was supposed to be a minus sign right here. Let's fix that right there. Yes, make that a minus sign. Okay, so if that's a minus sign right there, then that's going to give us negative 10 plus 10, which will give us 0. And then for the denominator, limit as x approaches negative 1 of x plus 1 is going to give us negative 1 plus 1, which is 0. None of that's even really the work. That's just setting up to show it's an indeterminate form. So that means that we can now take the derivative and solve. So for this one, we've got to do the limit as x approaches negative 1. And we've got to take the derivative of the numerator. So we've got to use a product rule for this part right here because we've got a 2x and an f of x. So we're going to use the product rule for that part. So we'll have 2x times f prime of x plus f of x times the derivative of 2x, which is 2, minus 5g prime of x. And this is all over the derivative of x plus 1, which is just 1. Okay, questions so far? Okay, now we've got to plug in negative 1. 2 times negative 1 times f prime of negative 1 plus f of negative 1 times 2 minus 5g prime of negative 1. We're going to get negative 2. Our f prime of negative 1, that's back up here. F prime of negative 1 was 1 plus, we need f of negative 1. F of negative 1 was 5. And then g prime of negative 1, that is going to be 4. So we end up with negative 2 plus 10 minus 20. So that is going to give us negative 12. Yes. Negative 12 per answer there. Okay. Questions? So, our homework from this comes very far into the work, and we are going to do page 551. Our book kind of holds off on doing L'Hopital's rule until much later, sort of the last thing. So it's actually, in our book, it's section 7.7. And we are going to do, let's see, let's do the 11 through so 11 through 39 odd. Actually, hold on. There might be a couple of these that are ones that we did in the notes. like 37 and 17. So a couple of them we may have already done. No, it's not 551. It's 511. Sorry about that. 511. So, go ahead and get started on those. It is several problems, but they should go fairly quickly, minus the annoying step that I do want you to write that limit of the top and limit of the bottom for me before you use L'Hopital's rule. I'll say use L'Hopital's rule for me on every one of these problems. Some of them you can do without L'Hopital's rule, but I would like for you to use it on every problem just to get that practice with it. There are a couple that have some inverse trig, like arc sine and stuff, so you might have to pull out that note card to